Good morning. My name is Hans Hersbach. I'm in charge of the C3S Global Reanalysis team. I'd like to thank all my team members and also people in the production of ERA5 and many people in the research department as well, and also outside ECMWF, because producing a reanalysis is something which involves many, many people and builds on many, many big shoulders. Okay, so just a quick, I will talk about the characteristics of ERA5, and then Bill will talk about innovations towards ERA6. So ERA5, where are we? It's a full observing system global reanalysis. Means that we try to get all the observations we can get our hands up and to use them into the reanalysis. It's for the atmosphere, land surface, and ocean waves. It's very popular. We have now actually more than 89,000 users, and it's growing a lot still. We have also daily, every day we add another day, 5 days behind real time. So we continue. It's an official product from 1959, but we are going back to 1940 now, and most of that has already been completed. You get hourly snapshot as a resolution, global snapshot of 31 kilometers. And we also have an uncertainty estimate that represents the varying confidence when you go further back in time of the product. We also have ERA5 Land, which is a downscaled product at 9 kilometers. So we use many, many observations, over 100 billion we have used so far, but we also rely on external gridded products as is, which is like sea surface temperature, CS cover, and greenhouse gases, aerosols, and these kind of fields. Okay, so strengths and the success of ERA5. So why is it that so many people use ERA5? That we think, why is that the case? So the strong thing is that ERA5 is the integrator of all the observations we have. So observations, they're scattered and not always easy to reconcile. And then the ERA5, it mixes all together and creates these famous maps without gaps, using a model, which is the model glue. And we try to do that in an as exact accurate as possible way. So the method we use is called data assimilation. So we also try to do that state of the art. So we use the latest, the best ECMWF model, which is then operational at the time, and then we scale it back at lower resolution because, of course, we can't afford to go 80 years at that high resolution. And we maintain it also close in real time. And last but not least, and it was already mentioned the previous presentation, it's also very important to make it available in a nice and easy way. So there's multiple classes of applications. This is kind of oversimplification. But anyway, so there's people, there's mostly scientists, they look at specific events or phenomena. So there you really need to know the actual weather of the day. It's important. Then there are applications of climate monitoring. So there you also need to know the synoptic situation of the recent past, or maybe the monthly mean, or things like that. But you need this consistent 30-year climate as well to know how different today is with yesterday. And then finally, there are these more purely climate applications where the actual weather of the day isn't that important anymore. But what is important is the mean state, the climate change, the low frequency variability. Okay, so we use many observations in ERA5, lots of satellite data, upper air data, surface observations. But if you have seen the YouTube video about reanalysis, but there is a problem. There's always these plots, but there is a problem. And we have a solution, of course. But it's the number of observations goes back quite a lot. So before the 80s, we have only a few satellites, not that much, and before nothing anymore. Before 1950, actually, we have hardly any upper air data. So if you then go back, you can still represent the weather in North America and in Europe quite accurately, because we have done case studies. There's Ulysses Storm in 1902 or something like that. ERA5 is really well in representing that. There's no problem whatsoever. But if you go to the Southern Hemisphere, of course, you don't know anything. But there you say, okay, for the actual weather, so people that want to know about the actual weather, they're a bit in trouble over the Southern Hemisphere. But for the climate, you don't really need to know the actual weather. You're more interested in the statistics. So we should still be fine. And in theory, we should be. But in practice, there are some problems. And so here, ERA5 suboptimal features. So, which is, what is really important is the systematic model bias. So, all models that have systematic biases. And of course, it's the task of the modelists to limit those to the minimum, but they will always be there, and we have to handle them. Because if you have, like today, we have so many observations, so our analysis fields, they are more dominated by the observations, the observed climate. While if you go further back in time, you need more model glue to combine all these observations in a dynamical way. But then the model climate is more, the analysis is more dominated by the model climate. And if they're not exactly the same, then you get shifts that are not the true shifts. Now, if you look at the troposphere for temperature, and in the lower stratosphere, then we are doing, I think, a good job at ERA5. But there's other parameters, and in this, higher up in the stratosphere, the hemisphere, we're actually not doing that. And we're working that to improve that. Then there's also challenges with respect to the NWT system that we use ourselves, like systematic errors, if for instance precipitation and energy fluxes. And there is all kind of smaller things that are quite local that we know about. And actually we maintain a list of known issues. I won't go into details. Then the uncertainty estimate. So the uncertainty estimate is actually for the estimate of the error of the day, and not about the mean state. So the error of the mean global temperature, this uncertainty estimate really gives an answer on what it is. And the spread is also too small. And there are some other issues as well. But I don't have time to go into all the details. And I'll let now Bill continue about ERA6 and how we're going to address a number of these problems.
Thanks, Hans. Morning, everyone. Just to remind you, ERA6 will benefit from 8 years of R&D at the centre since we first started ERA5, as well as benefiting from the larger compute capacity that we have. I think it's interesting just to reflect on the fact that those 8 years of developments are delivered by around 100 staff at the research department at ECMWF, around 20 staff engaged as external contractors, and around 10 engaged in related Horizon programs. So all of those developments are funneled through the reanalysis team, which comprises around 10 people. And our job is to adapt those changes and developments to run in reanalysis mode and to cover, for example, 70 years worth of analysis. So I think it's fair to say that the ERA6 will build on something like 1,000 person years of effort relative to ERA5, which is quite a thought. So what are those improvements? I've listed them here. We aim to run at higher resolution, so at least 18 kilometres. We've improved the model bias in a number of areas. I'll say more about that in the next slide. We aim to use observations more optimally and use more observations. We heard yesterday from Jörg and Paul on the satellite reprocessed data and the in situ rescued data, respectively. Another development that we expect to benefit from is all of the new sensors that have been integrated into the IFS since 2015. And we hope that will include the METOP SG sensors significantly. On the right-hand side then, the outputs of the CONFESS project will significantly improve our representation of surface forcings and radiative forcings from aerosols and greenhouse gases. We've got an improved ocean wave physics, which give us better representation of peak wind speeds in tropical storms and extratropical storms. And then there's a whole raft of developments related to the data assimilation schemes covering atmosphere, land, and ocean. So I really don't have time to do justice to all of these developments that are the product of hundreds of people's efforts. But what I can do is focus on just 2 of them to give you a flavour for what the issues are and what we plan to do. So if you look above 10 hectopascals, the forecast model propagates information from one analysis cycle to the next, and biases in that forecast model bias the analysis. Above 10 hectopascals, if unconstrained by observations, the model will run 2 Kelvin or more warm. So early in the period, this is showing anomalies from 1940 to the present, from the surface to 1 hectopascal. So early in the period where you don't have any observational constraints, the model simply runs warm. You then have a series of discontinuities as the observing system changes. And then only when you've got RO observations and numbers do you really constrain the analysis and get an accurate analysis. These problems above 10 hectopascals are long-standing. We recognize them instantly. But we've actually got problems in the mid to lower stratosphere as well, between 10 and 100 hectopascals. And in that region, the model tends to run cold by about 1 to 2 Kelvin. So again, where you've got no observations, you see these spurious cold spells set against the overall general cooling trend in the stratosphere. When we assimilated the first sounding data in the mid-1970s from VTPR, the way we bias corrected that data effectively reinforced the model bias. So we've got a spurious cold spell during the mid-1970s. And then later on, Peter mentioned the ERA 5.1 rerun. That was basically caused by the same cold model bias. So model biases causes problems. For ERA6, improved radiation scheme changes in the forecast model significantly reduced those biases at source. The implementation of weak constraint 4D VAR mops up the residual biases very effectively, and then the reprocessed observations will play their part in reducing the biases. I mentioned the use of satellite sounding data in the mid-1970s. That's indicated by this bar here. We have a contract with partners who are recovering all of the pre-1979 sounding and imaging mission data sets. The blue bars indicate those sensors that were recovered in the first phase of Copernicus, and the red bars indicate those remaining sensors, infrared and microwave, that will be recovered in the second phase of Copernicus. Now, that effort isn't simply recovering the data, reformatting, archiving, and documenting. It's really carrying out detailed assessments of the data quality and getting it ready for assimilation. Now, just to illustrate some of the work that's going on there, this is from Tom Hall at the University of Reading. When you look at that, when you look at the early imager data, in the polar regions there were problems in the geolocation. That was fixed in the first phase of Copernicus. We've actually also got similar geolocation issues in VTPR, which we already assimilated ERA5, and that will be addressed in the current phase, and they're making very good progress in that already. So finally, just to sum up, ERA5 is an hourly snapshot of the atmosphere for the last 70 years. It's widely used. We monitor it very closely, and we listen carefully to the feedback we get from users. Many of the challenges are related to the changes in the observing system. We've started preparing for ERA6 that will run at higher resolution. We'll address many of the issues that we've encountered, notably systematic biases and discontinuities. We'll make much better use of observations and do a better job of the uncertainty estimate. We take user feedback really seriously. We've got a number of mechanisms in place to capture that. But I would just say we're in the process of building ERA6. So if you've got any additional input, we're very keen to hear it. And if you're interested, there are some references there. Thanks for your time. Cheers.
Yes, sir. The mic is on its way.
You both mentioned the fact that the NWP system is tuned to the climate of today, but it is also tuned to the resolution of the operational model of today, which you said you degrade somehow because of economy of the whole operation, of course. Yeah. I wonder if there are any problems there in relation to a potential increase of the model biases because of the decrease of the model resolution, I assume without retuning, but maybe I'm wrong, transferred to the reanalysis.
Yeah, so there are some model biases in the stratosphere for temperature where resolution does make a difference. But to put it upside down, The kind of resolution that we run ERA5 in is typically the kind of the resolution that people in the research department do experiments with and optimize the system. And then when we go to implementation, then we go to higher resolution. So I would actually say that the resolutions that we use in ERA5 and maybe also in ERA6 are actually really well tested for that particular resolution. Yeah. Yeah.
Thank you.
Thank you very much to the both of you.